Is Andre coming as well?
Was it?
Is Andre?
Yeah, he knows about it, so I think he should get it.
We'll wait like a few more minutes. And then start.
We were out last night, so you might be a little slow.
So I'll introduce you. And then
Oh, you want to introduce it? Alright, that sounds great.
So how many people do we have Skyping in here? We have Francois?
No.
Start of March. What was that?
We have Francois with us? This is yours. And then
So this is mine, and then that's the YouTube community.
No, I see.
That's the role.
Yeah. Supposedly Dan's there.
Donc Adam il broadcast sur YouTube en même temps.
Oh là là!
For la
Oh là là.
But you get a special line.
So we don't know how many people really having
The whole world.
The whole world.
could be watching.
could be watching.
Blow it up on Twitter.
Can you watch it from your office?
Yeah.
You gotta complain. Start
commenting?
Do you know where Droid's office is?
Andre, I'll go
No.
check.
I'll get him.
Just gonna check something momentarily.
T'as encore 2 minutes peut-être pour...
Pas de soucis, t'inquiète. Je réfléchis aux spirales.
Quoi?
Je réfléchis aux spirales.
Ah oui.
Bah oui, j'ai lu, hein.
Aha! He's thinking about the spirals now.
Oh, yeah.
One more person hooked on the problem.
I know. It's not too late to play. The game is still going.
It's on a timer.
Oh, this is interesting. I like the advisor and supervisor. I thought they were synonymous. Now I know the supervisor is the one who actually supervises.
In Switzerland it's called assistant, which means like
Yeah, that's how it originally
assistant in
is.
French sounds very diminishing, but it's the real name in Switzerland.
Yeah,
For the supervisor?
yeah.
For supervisor.
If you know somewhere,
Anyone who's not a
just the
professor
assistant.
is assistant. Okay, let's get started anyway.
All right.
I'm starting. Okay, so good morning, everyone. Today we're here to listen to Adam, who will be presenting his work. The work has been going since March, I guess, so for the entire summer with us. So I had the pleasure to meet Adam a few years ago in Switzerland, where he was apparently my student in a class I was teaching, and then we worked together closely onto related law instability, a paper that was published last week. Okay. And since then, he has been doing an outstanding work here at MIT. And well, the floor is yours for doing this also.
All right. Thank you, PT. Dr. Brown. Everyone, welcome to the presentation of my master project, the surface topography measurements in the Bouncing Droplet Experiment. This is work in fulfillment of my Master's of Science in Mechanical Engineering at EPFL in Switzerland. It's being conducted here at MIT in the Fluid Dynamics Laboratory. My advisor at EPFL is Professor Francois Galler, who is on Skype today, and my MIT advisor is Professor John Bush, who's here as well. Additionally, I was supervised by Dr. Pierre Thomas. Now, an outline of what I'll be discussing today. First, I'll introduce the Bouncing Droplet Experiment, around which my project is based, and then I will introduce the methodology by which measurements were made of the surface in the system. Finally, I'll discuss those measurements as they apply to bouncers, walkers, and reflection phenomena in the Bouncing Droplet Experiment. And finally, I'll close with a potential theory about how the walker is interacting with boundaries. Now, this presentation will be about 30 minutes in length. It'll follow with an open session for questions, and then afterwards there will be a private defense with just the committee. Now, this phenomenon was first noticed in 1978 in an article of the magazine that is today known as Scientific American. Now, the question was, drops of liquid can be made to float on a liquid. What enables them to do so? Now, what Walker's setup was he had a fluid bath that was being vibrated by a speaker. And he noticed that as he dripped drops of fluid onto that bath, that they would appear to float. Now, with the human eye, that's what it appears is happening. But thanks to today's optics and high-speed camera, we can see that there's more to it. And that is that as the droplet is bouncing, there's a thin layer of air that is replenished with each bounce. Now, this layer of air that, as Walker predicted, separates the droplet and the interface from coming into contact. And as long as this bouncing continues, this air will be continued to be replenished, and as a result, it can bounce indefinitely. Now, in the experiment, we use silicon oil because that's very impervious to impurities, and with silicon oil, we can keep droplets bouncing for as long as a day. Now, for 30 years, this phenomenon was observed but not explored upon, until a group in Paris in 2005 discovered that in certain regimes, the droplets would appear to walk, as you can see in the upper video. Now, what's happening is that with each bounce, it's slowly moving from left to right across the screen. And one thing you can do is if you take what we call a strobed video, you can just capture the bouncer once as it's impacting the surface. And you can see it as if it's walking across the surface, which is why we call them walkers. And furthermore, if you notice where the crest is, it's as if the walker is getting pushed along by the wave. Now, this is for when the forcing acceleration is large. Now, if you keep increasing the oscillations of the vibrating fluid bath beneath the droplet, you'll reach what are called Faraday waves. Now, just introducing the forcing acceleration in the system, this is how we define the magnitude of the oscillations. The forcing acceleration is the amplitude of the bath oscillations times the angular frequency squared. What happens is if you increase this value enough to about 4.2 times that of gravity, you'll excite Faraday waves in the system. Now, Faraday waves need no droplet to cause waves. These will be excited naturally from the surface, as you can see here, and they will be sustained and grow. Now, because in this experiment, what we're interested in are the waves only produced by the droplet, in all the experiments and tests presented today, the forcing acceleration will be less than that of this threshold of Faraday waves. And furthermore, I'd just like to introduce the memory parameter. This is an important parameter that is a ratio of the forcing acceleration of a particular test to that Faraday threshold. And we call it memory because as the forcing acceleration is large, waves will persist longer in the system. So it's as if the fluid interface has a memory of the previous bounces of the droplet. Now also to just introduce some scale, the droplet size is about 1 millimeter, and the wavelength created by the waves is about 4.75 millimeters. And this is governed by the unstable wavelength of these Faraday waves. Now, to describe this system a little more, this can be thought of as what's called a pilot wave system. So as this droplet is bouncing, it excites fluid waves in the bath. And it's these sloped waves and the interface of that fluid bath that gives the droplet a trajectory that will make it move along. So since the interface is what determines the future trajectory, and the interface is a combination of all these waves, it means that a single drop isn't defined to just a single location at a single moment in time, but is instead a culmination of all the past bounces of the droplet, as well as the interaction that the waves have with these surroundings. And in that way, the droplet can be thought of as a spatially extended object, where the droplet just doesn't feel things that are very close to it, but can feel surroundings that may be 30 millimeters or more away from it. And then furthermore, something that's interesting about it is that if you confine the droplet to a corral, for example, as has been done here in the right by Dr. Harris, and what you find is that the long-term statistical behavior, if you look at its position as a function of time and plot the probability that it will be in a given position, you recover something, what is shown here, this probability distribution function, and this is similar to the Faraday wave equation. So this is the long-term statistical behavior. And now that I've explained this, I can also explain why this experiment has been so exciting in the last 10 years. And that is because it is analogous to quantum mechanics. Now, if you replace droplet with particle, the fluid bath with quantum vacuum, and the long-term statistical behavior governed by the Faraday equation with instead the Schrodinger equation, then you now all here have the basic foundations for understanding quantum pilot wave theory. And we can see as well, this is at the quantum scale, that if you look at the probability distribution function of electrons confined in a crowd, you'll get something very similar to what we see in the experiment. Now, science hasn't given us all the tools that we need yet to study quantum pilot wave theory at this subatomic scale, but fortunate enough as we are, it seems we have a pilot wave system that we can experiment with and do tests at a much larger scale, which is the Bouncing Droplet Experiment. Now, as for some specific motivation of my project. So if all you can see is the droplet, you're left in the dark. Because as I said, this is a pilot wave system where the two are constantly interacting with each other. So if we're able to measure and see not only the droplet but the waves, then we can get a complete picture of the physics that are playing into it. So that is the goal of this project, to see these waves in the system. And with that, we can hopefully elucidate reflection phenomena. We do not yet know what is the interaction between the wave fields and the boundaries in the experiment, but the first thing we can do is observe them and see what conclusions we can draw. Additionally, quality measurements of the wave field can build upon existing models and simulations. There have been many different models and simulations proposed to model this bouncing droplet, and without a knowledge of what the wave field looks like, it's hard to discern between what is a good model and what is not. And then the challenge of it all is that these waves are small, very small. They're between 1 and 20 microns, which is about 20 times smaller than the size of a human hair. So with that, the question becomes, how can you measure something so small? Which brings us to the methodology. For this project, I used the free surface synthetic Schlierian technique. It's a mouthful, but what it means is it's a method to visualize a surface topography between two fluids based on distortions of a background image. This method is simply how you know that there are waves in this pool. The waves of a pool have a very ordered and regular tiling, and you can see that in particular in the upper left that there are some deformations to that. Just from looking at it, we know that these deformations indicate that there are waves. And this is a very qualitative way to approach it. However, of course, there's a mathematically rigorous way to think about measuring a surface using this method. Now, let us just consider at first a horizontal surface. Consider a background image placed where this tan bar is at the bottom, and consider a fluid placed upon it. Now, the fluid layer above the background image, as well as the air, have to have different indices of refraction. And why this is valuable is that as light passes through the interface, it will be refracted. And that change we can use as a deformation to gauge what the surface looks like. Now, there are a couple of assumptions that must be made if we want to apply this method. One is weak amplitude. That the amplitude of the waves on the surface are much smaller than that of the fluid layer that is above the background image. Now, fortunately, as I just discussed in the previous slide, these waves are very small. So that criteria is certainly met. Additionally, there's the approximation of weak slope, that at no point the interface is too large. Now, as I said, the waves are small, and also this wavelength is fixed to a value that is 1 to 2 orders of magnitude larger than the height of the wave. So as a result, weak slope is verified in the system. Finally, the paraxial approximation just says that the camera is far enough away from the light rays that are coming to it such that they can all be approximated as coming in at the vertical. And this is satisfied just by placing the camera far enough away in the experimental facility. So as a result, based on these 3 primary assumptions, it appears that this experiment is a perfect candidate for using the free surface synthetic Schlierian technique. Now, instead of a horizontal surface, let us consider one that now has a slope to it. So Snell's law will tell us how the light is refracted, and once there is a slope to it, we'll get an apparent displacement. So if you imagine this point, this small black square, when the surface is horizontal, it will have an apparent location coming from the vertical gray line extending up from it. Now, as this slope begins to curve, you see that with respect to the camera, it now has an apparent position a little bit to the left. Now, using Snell's law, as well as the approximations we introduced earlier, you can relate what that displacement is to the gradient of the interface, which will give you the slope. And then finally, taking the inverse gradient operator on the displacement field, you're then able to recover the height of the fluid bath anywhere in the experiment. So now that we have that, the question arises, how do we get this displacement field? Now here's some raw data from the experiment. While grids, like you saw in the swimming pool, are nice for humans to see, this random dot pattern is much better for computers to pick out. Now, you see on the left a horizontal reference image, and whether you believe me or not, the right image is a distorted image. Now, the distortions are very small, which is why you probably can't make them out, but it's still enough for the computer to pick out. So how can we figure out what this displacement is from something like this? And for that, we use particle image velocimetry. Now, particle image velocimetry was developed for a very different application. It was developed to look at fluid flows. By having a fluid flow and using seed particles, you would be able to take a video of it and then track the movement of those particles in time. And that would give you an approximation of the flow field. So while this is very different, the same tools and methodology that have been well developed for this one case can be used in this experiment. So what's done with those raw images is there are many interrogation windows that are laid down, here demarcated by that blue square. We first select an interrogation window in the horizontal reference image, and you see where it best correlates to a point on the distorted image. You take those two locations, and that'll give you a displacement vector for that given change of the interrogation window. We did this many times, and that'll give you an entire displacement field for two images that you have. So again, the horizontal reference image, that's one that you take when the surface is completely horizontal, and there's a distorted one that you'll arrive at when the surface has waves upon it. So once there's the displacement field, you can then perform the inverse gradient, and then you'll eventually arrive at a wave field of the surface in the experiment. Now, this is a bouncer, and I say strobe because it's also a video, which I will play now. And by being strobe just indicates that there's being one image capture per cycle of the bounce. What we can see here is they reach a height of about 10 micrometers, but it's much more than just visualization. So with this data, we can do interesting things. And one of the things that was done was to generate the wave profiles. Now, one of the things that was done for bouncers was by taking the ISO contours, it was then possible to identify the circular patterns in them, and from that, identify where the center was. If we knew where the center was, assuming that the wave field is axisymmetric, as it should be for a stationary bouncer in one place, then we're able to reduce an entire 2D wave field down to a single wave profile. And this corresponds to the maximum amplitude for this one particular bouncer, shown in the video previously. Now, this is very valuable for just a single image like this is very valuable for numericists to compare their models. And also one thing that can be done is by changing the capture phase, so where the bath is at the time when you take your video, you're able to recover the time evolution of a bouncer in the system. This is the wave field as a bouncer is bouncing. Now, one of the things you may be wondering is there's no droplet in this video, and why is that? Well, firstly, because the droplet is not consistent with the horizontal reference image, the inverse gradient acting upon that and trying to use PIV to figure out what the wave field is looking like under the droplet is impossible. The droplet acts as kind of a barrier, so you can't see what's underneath it, and it also, due to interpolation and smoothing, you can't really trust the data within 2 millimeters of the center. However, that's very small in comparison to the field that you're looking at now. So while we can't know where the droplet is based on this method, neither what the wave field is beneath it, based on the surrounding wave field, we're able to extrapolate back and get an idea of what it should look like. Now, besides just a time evolution of the wave field, other results that have been carried out in this project have been the effective memory. So by increasing the forcing amplitude, it was found that the amplitude of the waves increases as well. And then also I mentioned that this is valuable for comparison to simulations. One of the best simulations out there was compared with this model, and I'll play a video of the time evolution of the wave profiles and how they compare. Now, there are some slight amplitude differences. However, there are more similarities than there are differences. There's very similar spatial decays, as well as the propagation of the waves as they expand out is very similar. And this has been very valuable in comparing models, and many more comparisons shall be used in the future.
Which is the theory which is experiment?
The experiment is in blue, the theory is in black. So increasing the complexity a little bit, let us now discuss walkers. So here's the wave field of a walker as it crosses the screen from left to right. Now the waves are about double in size of the video that you saw previously, and now the spatial extent of these waves is much larger, as the spatial decay is much less for a walker. Now, in the case of very low memory, the bouncer or the walker will move across the wave field and produce a wave field as if it were a bouncer. It's very axisymmetric, and it's just as if it's that circular wave field just being translated across the plane. Now, on the very other end of the spectrum, at high memory, very close to the Faraday threshold, what you will find is a walker that leaves behind these deep tracks that are nearly invariant in the direction of the droplet travel. So, just play it again. And these waves persist much longer than the waves that we saw in the low memory case, which again ties back to memory and how long the interface remembers what previous bounces were. Now, taking somewhere in between this low memory case and a high memory case, we get a wave that appears to be a combination between the two. I'll stop it here. And what you can see is that you have the rings that you saw in the low memory case, and you also can kind of visualize these deep tracks that we saw in the high memory case. So this checkered pattern that we get in the wake of the walker appears to be a combination of these two behaviors. And just to give you an idea where we are at on the scale, here's where these videos were recorded as a function of memory. And then also comparing them side by side, it's easy to visualize how this transitional memory is a combination of the high memory and low memory cases. And I'll revisit this later in the presentation. But now I would like to move on to interactions of the walker with a boundary. Now, if we were to put an obstacle that was going through the fluid surface, this would create a meniscus. And as the fluid bath would be vibrating, this meniscus would vibrate and it would create its own waves. Again, what we're interested in is the waves produced by the droplet and nothing else. We're interested in its interaction, these waves, with boundaries, but we don't want the boundaries themselves to be creating waves. So as a result, in the system, all boundaries are submerged slightly below the surface so that they don't create their own waves. But this, with them being so close, this will dampen any waves above them, and it will also prevent the walker or droplet from passing over them. Now, in these experiments that were conducted in my project, this height above a barrier was set to 0.3 millimeters. Now, one of the first types of boundaries that we looked at was a pillar. So this was a submerged circular boundary that was slightly under the surface. And what we found is, surprisingly, that as we were directing these walkers towards a pillar, we found that it would first be repelled, but then it would hook back and kind of loop around the pillar. One thing I'd like to point out also while we're here is if you notice the white rectangles on the right of the image, those are what we call our launcher. It's the means by which we can direct a droplet in a very specific way. And this is just two planar boundaries submerged under the surface. And the droplet will straighten itself between them and be directed along. So now coming back to the pillar, this was very unique and curious when Dr. Harris found it. And so he investigated it in terms of memory. And it was apparent that as the memory was increased, that it was more than just hooking. These were in fact spirals. And the largest spiral that you see that loops around the longest, this corresponds to a very high memory, very close to the Faraday threshold. And what happens is as you step down from that and decrease the memory, the spiral unwraps from around the pillar. Another suite of experimental parameters that was conducted was in terms of different pillar sizes. Different pillar sizes of 3 millimeters, 5 millimeters, and 15 millimeters were tested. And ones corresponding where the pillar was smaller, we would see a smaller growth rate. The trajectory corresponding to a 3 millimeter pillar is the one shown in turquoise here, and that grows until the one shown in yellow here corresponds to a 15 millimeter diameter pillar. So that was one observation that the growth rate increases, and that will be revisited as well. Now, besides just showing trajectories, there's some analysis that can be done. And one way that you can consider these spirals is in terms of their heading direction. Now, the heading direction can be defined as an angle between the trajectory that the droplet is traveling at and its deviation from what would be a circle with a center at the pillar. Now, what you find here is the graph shown at the right with different regions indicated corresponding to the figure shown on the left. So there's the approach region, region 1, and then as it approaches that pillar, it eventually will receive a bump, which is region 2. And it will be repelled from the droplet. It will have a very large heading direction, and then that large heading direction will slowly come down and then stabilize to a constant throughout the spiral, region 3. And then eventually, once the walker is no longer feeling the effects of the pillar, it will break off from the spiral and travel in a straight line, which they typically do when they are not feeling any boundary effects. Now, one exciting thing about this is you can see that in region 3 that defines the spiral, the heading direction is constant. Now, if you investigate this parametrically and consider an object moving at a constant velocity, if it also has a constant heading direction, it necessarily is following a logarithmic spiral. And this is very exciting because logarithmic spirals are ubiquitous in nature. You can find them everywhere, from nature to weather patterns. And however, as ubiquitous as they are, we never expected to find them in the experiment. So this is very exciting. Now, I would just like to mention there are some deviations from logarithmic. The logarithmic fits best as you are farther away from the pillar. So sometimes when you're close to the pillar, you'll see some deviations from that. So logarithmic fit is here shown in magenta, and as you're closer to the pillar, sometimes it appears to align more with a different type of spiral, possibly Archimedean, possibly a different style. However, that's where you will see some slight deviations. Also worth mentioning, the trajectories and spirals corresponding to spirals with a larger pillar size will tend to have a slightly better logarithmic fit than those with smaller pillar sizes that are more tightly wrapped around the pillar. So now there are many observations, so this is a perfect opportunity, as we don't yet know what's going on, to apply measurements of the wave field at the time. So I'll play a video, I'll let you watch it once, and then I'll play it a second time and pause it partway through. The pillar is indicated by the orange circle, and you can see as the walker is reflected from it and spirals. Alright, so now the second time the walker comes close, it gets bumped away, and then it locks into this spiral trajectory. Now, one thing that has been noticed is that normally the largest wave amplitude is those right around the droplet, and additionally, you'll have very large wave amplitudes coming off from where the wake edge is behind the droplet.
What's the blue line?
The blue line is just slightly indicating what the trajectory is. You can kind of follow it along and see how progressively through time the wave field still aligns, as if you had a walker kind of traced along the trajectory. Now, you see these dominant waves extending out from the wake edge, and as I continue to play it, pay attention to how this wake is aligned with the pillar. One thing that was found using this method is it appears as if this wake edge is tethered to it and always tangent to the pillar. And this could be an indication of where the dominant physics might be governing the spiral trajectory. So if we continue a little more, you can see how it stays attached to it as it marches out its spiral. So this is exciting, but admittedly it's not what I was hoping for. I was hoping that applying this method would immediately give a very clear and obvious answer of why we're getting a spiral. And while it didn't do that, it does show an indication of maybe what could potentially be some dominant physics, the fact that this wake is always tethered to the pillar. So now this corresponds to a very simple geometry when you have a pillar. And now I'm going to transition to another simple geometry, just a plane barrier. Now, the motivation for this was in experiments conducted by Dr. Harris, preferred angles were observed when a walker would pass through a single slit. Sometimes the walker would go straight, and other times it would deviate to either the left or the right. Now, motivated by more curiosity, he decided to place just one barrier, and instead of two, and just have a walker that would pass by a wall. And what he found that this preferential angle was still observed, where the walker would walk forward and then curve. So his thought was that maybe this diffraction to left and right wasn't due to any interactions with the wave field and the slit, but was more the walker trying to align itself to a preferential angle of travel with respect to the barrier. So, as part of this project, I investigated the same, but in as simple of an experiment as there could be, just a single plane wall, and I directed droplets towards this, towards the planar barrier, investigating three things. Pay attention to the angle of incidence, measured with respect between the trajectory and the wall. I paid attention to how close the trajectory becomes to the wall, and I also paid attention to the angle of reflection. Now here is the ensemble of data. On the y-axis is shown the angle of reflection, and on the x-axis you have the angle of incidence. And one thing that I'd like to first note is that this dashed gray line would be as if you had ideal snow reflection, where if you bounce light off a mirror, the angle at which it reflects is going to be approximately equal to the angle at which it is incident. So one might expect that that's where all of our data would align at. However, what we find instead is exactly what Dr. Harris found, where there seems to be a preferential angle of reflection, which I would just label here the lock-in reflection band. So excluding some cases where testing is difficult for experimental facility reasons, and excluding cases where the angle of incidence is directly to the plane barrier, what you'll find is that for a very large range, you will observe a single preferred angle of reflection that is anywhere from 20 to 30 degrees. It all kind of falls in this band. Now, to give an example of what the trajectories look like in this band, here are just a select number shown, collected from that magenta stripe that you saw before. And you can see here that all of these coming from the left and going to the right, that for a variety of angles of incidence, they all kind of lock in to this one angle of reflection. Now, one thing I haven't discussed yet about planar boundaries is the effect of memory. And just setting the angle of incidence to a single value and sweeping the memory, you can find that there is a slight increase. Now, the low memory, corresponding to about 90 degrees, corresponds to when this is smallest, and the high memory, corresponding to 96.5% of the Faraday threshold, corresponds to when the angle of reflection is largest. So the change is very slight. However, there is a continuous change as a function of memory. And one thing also worth mentioning is that even though it's changing, these all fall within that preferred reflection band that I had indicated earlier. So now what more can we learn about these observations through the use of measuring the wave field? So here is a walker as it approaches a barrier. The barrier here is indicated by that orange line that you see. I'll play it once more and stop it as well. Walker goes, reflects from the boundary. And here we can see something interesting. So one thing that it appears is that maybe this wake could be aligning itself in some way with the wall. Could that be what is causing this preferential angle? You have your wake angle, and then you have the angle of reflection. Could there be some relation between the two? Now, I was initially hesitant to prescribe this preferential reflection angle as a function of this wake angle, because the wake angle isn't constant. The wake behind the walker is curved. However, then I realized that this curved wake edge is not a problem. It's the solution. So now I'd like to present wake alignment theory, which is my theory for how the droplet is interacting with boundaries. So first, considering how the wave field can be thought of a combination between a low memory case and a high memory case for a walker, we can first pay attention to where the antinodes are in this wake. And an antinode corresponds to where you have a maximum and a minimum aligning together. Now, you can write an equation that will give you the location of all these antinodes, but we're not interested in all of them. Here we're just interested in the ones that define that primary wake edge, where n equals 1. What you do is you can get an equation defining what that wake edge would be, where here the parameter VW is the velocity of the walker, and TF is the period. And also the values correspond to x being this horizontal and y being in the vertical.
Primes?
The primes just are used for notation because I'll be introducing another x and another y here shortly. And also I will mention that these have been non-dimensionalized with respect to the Faraday, half of the Faraday wave. So now, once we have that, we can pose a question. So imagine that this wake edge behind the droplet, shown here at the origin, is making some preferred angle alpha with respect to a barrier. Okay, so if we impose that, we can find not only alpha, but also this angle beta down here, which is defined here on the left, and its relevance is shown here as we look at it in terms of the trajectory that it's sweeping out. So what we'll find is that this angle beta will be relevant as you're able to retrieve the trajectory of what this wake alignment would give just by integrating the tangent of beta along the trajectory. So now the question is, what do you get when you do this? So here's a trajectory from the experiment of a walker being reflected from a planar boundary. And when you use wake alignment theory, you get a trajectory that is strikingly similar. Not only does it recover the preferred angle of reflection, but it also gives you the curve leading up to it, which before this was not addressed. Now, in this, there's one free parameter, alpha. That is what angle does this wake edge appear to lock into a boundary. And I will say that this theory is very young. It's less than a week old. So there have only been a limited number of comparisons between actual trajectories and this theory. However, initial comparisons show that there's a lock-in fit for alpha equals 75 degrees. Now, of course, we don't like...
Can you go back to the diagram so we can see alpha?
Yeah, sure.
Here's
So alpha is right here, which also corresponds to where it's locking into this boundary. Okay? So, of course...
So 90 minus 75 would be the 25 of the back.
Yeah. Well, actually,
yeah.
no, actually, no.
Say it very fast.
So that band angle
Sorry.
is what beta gives.
beta.
Beta gives you that.
Sorry,
Well, the view was straight.
to say it's a free parameter, I mean, it varies from no bounds.
It doesn't vary. And so the alpha is unknown. I don't know what it could be. So plugging in different values and seeing what best fits the data that I have. And it's 75. It's a free parameter of this theory. But of course, we don't like free parameters. And fortunately, due to the surface measurement method that I've implemented in the system, we don't have to take this free parameter. We can measure it in the experiment. So here's a snapshot of the video that I showed previously. And from this, we can define where the wake edge is. And we can actually measure this angle alpha in the experiment. What do we do when we get that? We get that alpha equals 76.7 degrees, which is very similar to what is predicted by the trajectories that leave from that arise from a walker being reflected from a wall. Now this extends beyond that. There are many things that this would explain if we accepted this wake alignment theory. One is that the curved trajectory immediately after a reflection from the wall is explained as part of this wake alignment. Additionally, it explains why we have variance in the measured angles of reflection. If instead we stop thinking of them as just single straight lines where there's a single angle that can define them, and instead think of that as a curved trajectory, you can not only explain them more, but you realize that if you do define them as just one angle, drawing your attention to the figure here on the right, this is the heading direction as the droplet is moving away from the planar barrier. And what you find is that it is constantly leveling out. Now, when I was measuring the reflection angle, not knowing that it was changing, these measurements might occur anywhere from 3 centimeters to 6 centimeters away from the planar barrier. And if you look at what that gives you based on the theory, that would indicate that I might get measurements anywhere from 20 to 30 degrees in the reflection angle. So this explains the preferential angle of reflection as well. It also would explain why there's a slight increase in the angle of reflection as a function of memory. As the memory increases, as does the velocity of the walker, and this will close up that wake slightly. And that slight closing of the wake would explain why there seems to be a slight increase in the angle of reflection. It also explains why using two planar barriers, as we do for launchers, works so well. And a droplet will perfectly bisect it, because it's simultaneously trying to align its wake to both of these planar barriers. Now, if I can extend it a little bit further, I don't have a good theory exactly what it might be aligning to for a spiral, but if you do propose that it is alignment with the wake edge as opposed to anything else, what it would explain is why a spirals deviate from a logarithmic spiral early in the trajectory. As shown here, the heading direction starts large and then collapses down. So in this first region, you're not going to get something that's logarithmic because the heading direction isn't constant, which I said was a criteria for logarithmic spirals before. And this is exactly what we've seen, whether you try to fit the trajectories to a given spiral, or if you just look at the heading direction of those spiral cases. If you recall, it started high and then came down before it leveled out. Now, also this would explain why spirals with small growth rates have the worst logarithmic fit. And this would be not necessarily because of the growth rate that they have, but just that throughout their spiral, they're staying closer to the pillar, where you're going to have heading directions that are less constant and change more. So just to close, free surface synthetic Schlierian method was used to measure the surface topography in the Bouncing Droplet Experiment. This was applied to bouncers, which was a wonderful tool for numerical simulations and models, and also was a really good time to get out some of the kinks in the methodology as I was implementing it. Walkers were studied, and they offered an insight as to the wake behind a walker and what causes its formation. And then additionally, this method was used to analyze reflection phenomena, which hinted at dominant interactions between walker and boundaries. And then finally, I introduced my wake alignment theory, which is a synthesis of all the observations seen throughout my time here doing this experiment. So thank you very much. I'd like to first say thank you to all the people that helped. Even though I'm up here alone, I'd be misleading you to have you think that this wasn't a group effort. There are many people that contributed, brilliant researchers without whom this project would not have been possible. And then I would like to thank both my advisors as well as all of you for attending, and all of you who are watching online at the live broadcast as well. So thank you very much for your attendance, and I'd like to open the floor to open questions from the public.
So we're going to turn off the YouTube now, or you can leave it?
They can see open questions. And then
it's going to go on and on, because I need to understand your wake alignment theory. So maybe if anyone else has any shorter questions, they can start.
Well, I think we're going to close it to the committee after open questions.
Okay.
So then we can
Okay,
go
yes,
on.
very good.
Yeah.
I have one question.
Yeah.
When you do that horizontal reference image, is this view like move around the camera? Do you correct for the fact that like, there are different lengths from the surface to the live camera? Like,
Mm-hmm. Yeah. So I showed a simplified version for this presentation to just kind of capture the physics behind it. However, there are ways to go. So if you actually, in the actual method, you're not comparing just this apparent displacement in the horizontal case, but you take into account the change of the apparent location when it's horizontal, and then the apparent change as the slope is surfaced, as the interface is sloped from all angles considered. So you do the calculation here, and you take into account the geometry of it at all angles. So,
but you never move around the camera.
no, but you're still far enough away such that you can make small angle approximations on the angle coming in. So it's about 1.3 meters away, and the imaging area is about 45 millimeters. So.
And does the optics play a role?
So the Well, first off, you don't need very fancy optics, which is a real advantage of this method. You can use just your basic camera. But you do, again, you have to be far enough away. You have to be able to observe the image with enough resolution such that you can put down enough droplets or dots in your background image to properly resolve the gradient field. And then also there are some things that have to be taken into account, such as any vibrations of the camera between the camera and the background image. Slight vibrations as small as 0.5 millimeters will correspond to a pixel in shaking, and this has to be filtered out later. So there is some filtering that goes into this to take into account vibrations in the system.
I have a question about the spiral measurement of the waveform.
Yeah.
So on top of the pillar,
Yes.
do you have a dotted pattern up there, and how good is the measurement of the wave on top of the pillar? Is it flat as we see it, or do you don't really have a measurement?
So, well, I will first say that the waves that you see in this image, in this video, are representative of the waves that are in the wave field. And how this was done is that typically, while our barriers that we use are metal, in these cases, all barriers and boundaries, both planar and this pillar, were clear acrylic, so that you could still use the methodology through and see what's on top. And then, and the waves that you see here are as they appear. There is a slight difference between, because you have different indices for refraction, different thicknesses of the layers, there would be a change that has to be taken into account, and this is considered.
What's the amplitude of the noise there? Because you can see some background.
The amplitude is about 2 to 3 microns in these images.
The amplitude of the noise?
Of the noise, yeah. Yeah, and where the amplitude of the wave goes as high as 25.
I see.
So,
So for Lucas' question, could you show the planar reflection again and highlight how much waves are penetrating inside?
Yeah. So, I haven't made direct measurements. This would scale to probably around 2 or 3 millimeters into the planar boundary. Now, this method was applied for planar boundaries in one cases by the group in Paris. They found that they propagated in much more. However, they were using a much higher fluid height above the boundary, which would explain that, since a shallower barrier tends to dampen out these waves more. Yeah.
I have another one. For the planar barrier, you said you measured the delta, the distance where it turns around. Any observations on that? Or?
There were. I cut them out for time. However, I have them included as well. So this closest approach distance, it was found to vary most with the angle of incidence, and very, very well. However, the interesting part about it all is that if you do a histogram of all of the data swept as angle of incidence, then what you'll find is that you'll find peaks corresponding at quantized at about half Faraday wavelength intervals away from the planar boundary. And this half wavelength is exciting because it can be thought of as an indicative of reflection, because unlike just a typical sine wave, if you have a sine wave reflected upon itself, it'll be repeating at half wavelength intervals. Yeah.
So I know that the wedge is curved, but could you give us a brief estimate of what's the typical angle or apparent angle?
Yeah, so measured close to it, this apparent angle will range from, it goes up to 120, so that would be 60 on each side. And then it starts much lower than that, maybe closer to 90. Yeah, right, so that's, there you go. So it starts close to 90, maybe a little smaller,
Far
and then
away, it's roughly 120.
the 3 wavelengths, that was, I think, what I was measuring.
175.
No, 15 again.
Can we go to your plot where you have the form of the, what you feel is a function of memory?
Yeah.
There we go. So, are these, so we know that there are different modes of walking. So you have resident walkers, you have chaotic walkers, you have more complex periodic walkers. Can you see any indication of the periodicity of the bouncing in the weight?
Not very well.
So
So
you can see some oscillations, right?
yeah, so it does this center peak, and in particular in the high memory cases, it does seem to be more jittery.
So those
Yeah,
are
sure.
chaotic walkers, probably. Yeah.
They probably are, because this is something that is more seen at these higher memories.
Right.
But I would be hesitant to define saying that that's what it means, as it's hard to trust the data immediately around where the droplet is. So if that peak is moving, it could be that.
But so are you working in operating in a regime that Jan has explored and Oystein, so they did the map,
Mhm.
and so you can actually pick off. And yours,
So
what the
This would
viscosity
be-
and frequency are you running at?
I'm 80 hertz viscosity, 20 CST,
Right. So
and
that's
vibration number 0.8.
right. So we should know
So it's on.
then whether it's
Mm-hmm. Yeah.
worth noting, no?
Yeah, so this is a chaotic bouncer.
Yeah.
certainly. And for those who are not familiar with some of the terminology, a periodic bouncer will have a bouncing period twice that of the driving period, and a chaotic bouncer will maybe bounce like that sometimes, will bounce at different impacts. Each time it bounces, it'll be at a different phase, so the trajectory is not a nice periodic cyclical trajectory. Any more questions from the audience? All right, well, thank you for attending, and I'll kick you all out and turn off the live broadcast and close it down to your private defense.
All right. Thanks a lot.
Thank you.
No, but